Hi, welcome to this video on learning to solve exponential equations by rewriting with the same base. Now, just remind ourselves a little bit what an exponential equation is. It's any equation where the variables are contained within the exponent rather than down here. So this is an exponential equation because the variable is contained up here. So ironically, we aren't going to need to rewrite with the same base because remember the base of an exponential is the thing being raised to a power, and they already have the same base. So here's a problem we were given that the base was already made the same for you. So basically, if I said 5 to the 7th equals 5 to the what? What would have to go into that box in order to make it true? Well, if these bases are alike, then whatever's in here has to be equivalent to 7, or else it wouldn't make sense. Well, that's the kind of idea we're going to use here. 5 to some power equals 5 to some power only if these powers are equal to each other. So since these match, I'm going to say, you know what, 2x plus 3 has to be equal to 11. And then you just solve it like any old Algebra 1 student would. 2x is equal to 8, and therefore, excuse me, dividing by 2x ends up equaling 4. If you didn't believe that this was accurate, excuse me, if I put a 4 in right here and found out what 2 to the 2x plus 3 is, it would come out the same as that would as well. So there you go. There's the most basic form of this, and it's already been rewritten with the same base. Let's put up one. You want to take a screenshot, feel free, but all I did was, once I knew the bases were the same, I said the two exponents need to be equal. Let's try another one. Anytime you want to take a screenshot of a board that I filled up, you're welcome to go ahead and just screenshot it on your iPads, and it'll be something you can add to your notes. Here's example 2. This one I'm going to make be 2 to the 5x plus 10 is equal to 8 to the 4x minus 3. This is an example of one that the bases are not alike to begin with. So we're going to have to rewrite it to the same base. Let's take a look at 2 and 8. I think I know a way to write 8 as 2 to a power. So I'm going to leave this like this for now. And I think I'll write 8 as 2 to the 3rd. Do you all agree that that's just a fancy way to say 8? We can't just throw this away. But basically, 2 to this power is equal to, and this has been rewritten with a 2, but it's really just an 8 to that same power you see there. Again, we know that something to a power raised to a further power, I can multiply the exponents. So this is going to look like 2 to the 5x plus 10 is equal to 2 to the, and I'm going to multiply this through. Make sure you multiply one term by two terms the same all the time. So that's a 12x minus 9. Now do you see I've maneuvered them both into the same base? So there's no way this could be a true statement unless these two exponents were equivalent. So that's where I finish. I say 5x plus 10 must equal 12x minus 9. And then I solve it like any good Algebra 1 student. I get my x terms on the same side, I get my number terms on the same side. It doesn't really matter which sides you settle on. I usually would have brought it over to the side that didn't make one of them negative, but I have a negative 7x plus 10 equals, and then I have the negative 9 remaining. And I'm just about to the end of my board. So at this stage, I'll just carry up the process here. I got negative 7x plus 10 equals negative 9. And now I'm going to subtract 10. So that will give me negative 7x is equal to negative 19. And this number is not going to be friendly. We'll divide by negative 7. We'll get x equals this. Negative over negative is positive. 19/7. What a crazy looking value for x. But it doesn't matter. That's what it came out to be. So that's how you handle it when these do not look alike. You look for a way to rewrite with the same base. I knew of a way to write 8 was 2 to a power. And then I carried out the calculation. Go ahead and take a screenshot of this. We'll do one more. Screenshot, anybody? Okay. So we're just going to do one more example of this type. So this will be example 3. So if I had something like 4 to the 5x is equal to 8 to the 3 minus 2x. Okay, that'll work. Now this is a little bit different than the last one we did, because just like in the last one we did, these were not matching. We're going to have to get them to match. But I don't think I know of a way to write 8 as 4 to a power. There is a power out there that 4 raised to that power would land on 8, but it's not a friendly integer. So unlike the last problem where I kept one of them as 2 to some power, this one, I think I know a way to write this as 2 to the 2nd. So I'm replacing this 4 with 2 to a power. And I know, just like last time, that 8 can be written as 2 to the 3rd. So can you see that I replaced the 4 and the 8 this time, both of them, with the same base? We need to get this is really technically still a 4, so I'm going to use my property of exponents. Something to a power to a further power, you multiply. 2 to the 10x is equal to 2 to the, and here we have a single term times a binomial, so you have to distribute. So 2 to the 9 minus 6x. And now, because these match, I can say 10x equals 9 minus 6x. At this stage, I'm going to get x alone. I think I'll add 6x to both sides. And I'm going to write the result of that up here because I see I'm off my board here, off the view. So 16x equals 9. And now we just divide by 16. And x is this really friendly number, 9/16. We don't worry about the values coming out ugly. We don't worry about leaving answers in fractions. In fact, with a lot of these, if you were to do the division out, you would get ugly decimals and you'd have to say, how many digits do I keep? Why not leave it as a fraction? I hope this video has been helpful.